Welcome to part 2 of the lecture on cyber AI and specifically on the AI portion of cyber AI. That's our focus, although we, of course, tie things into cybersecurity throughout. In part 1, we talked about supervised learning. Well, we defined machine learning and then talked about supervised learning. In part 2 here, we're going to talk about unsupervised learning. And remember, with supervised learning, the idea is that we train a model using labeled data. We have examples where there are right answers, and we know those right answers in advance. But real life rarely gives us clean labeled data sets, and cybersecurity professionals face mountains of raw logs, network captures, executable files, DNS queries, and more. There's no clear indication of which are normal traffic and which are malicious. Well, that's where unsupervised learning becomes essential. Unsupervised learning is about making sense of data without labels. That data without labels is important. Instead of training to predict a known outcome, we let the algorithm explore the data set and reveal patterns that were hidden from us. Think of it as turning the lights on in a dark room, and that dark room is filled with unfamiliar objects. You don't know exactly what's in there, but unsupervised learning can help you start grouping, organizing, and highlighting the unusual. This part of the lecture, then, we're gonna talk about building some unsupervised learning. We're going to talk about how what unsupervised learning is and how it differs from supervised learning, and most importantly, how it applies to cybersecurity. Here's how we'll proceed. First, I'm going to define unsupervised learning in hopefully plain terms, and then we'll dive into its two main categories: clustering and dimensionality reduction. These are the two workhorses of the unsupervised world. Next, I'll walk through the extended cybersecurity applications. We'll take time to build some concrete scenarios, anomaly detection, and maybe insider threats. We'll talk about those. After that, we'll explore some case studies as well, and we're going to talk about some of the limitations around unsupervised learning as well. So first off, what is unsupervised learning? With unsupervised learning, it's really data without labels. There's no ground truth to check against. Instead of telling the model, this is malware, this is safe, we simply feed in the raw data, the traffic flows, the system events, file features, and so on, and metadata about the file, and we ask the algorithm to find structure. The goal could be to identify clusters of similar behavior, to detect anomalies that stand out from the crowd, or to reduce the overwhelming complexity of highly dimensional data into a simpler, more interpretable form. With clustering, it's one of the most natural and powerful ideas in unsupervised learning. The word itself tells you sort of the story about what it does. It's one of those few times in computing where the word actually means what you might think it means. We want to find clusters or groups of data points that are similar to one another without being told in advance what those groups should be. So unlike supervised learning, where we already know the categories, clustering is about discovering those categories, or more generally, just about discovery. So imagine dumping a box of puzzle pieces onto a table. You don't know, and you don't even know the picture on the box cover. You don't necessarily know what that goal is, but as you spread the pieces out, you might start noticing that some pieces are mostly blue, maybe they belong to the sky, some pieces are green, maybe they belong to some grass. So without being told the categories, you're clustering those pieces by their similarity. Maybe you find corner pieces first. Whatever your strategy is for working on a puzzle, you're clustering those together. The mathematics underneath clustering, of course, is rich, and there are many different approaches, each with its own strengths and weaknesses. So let's look at the three most common means for clustering. The first one is k-means clustering. Often the very first clustering algorithm that students learn because it's conceptually straightforward. The idea is to choose a number, k, which represents how many clusters you want to find. The algorithm then randomly selects k centers, selects that number of centers, and assigns each data point to the nearest center. After that, it recalculates the centers by averaging the points assigned to them. This process repeats until the clusters stabilize. K-means is fast. It works well when the clusters are roughly spherical and equally sized, but it has limitations. You have to decide what K is in advance. You have to decide how many clusters that you want in advance. It's not always obvious what that might be. And K-means also struggles with oddly shaped clusters, for example, clusters shaped like long spirals. dbScan, or density-based spatial clustering of applications with noise, is a different approach. Instead of asking for the number of clusters up front, it looks at the density of points in the dataset. Where it finds dense regions, it declares a cluster, and where points are scattered sparsely, it labels them as noise or as anomalies. That makes dbScan especially good at finding clusters of arbitrary shapes. For example, if your data has crescent-shaped or elongated clusters, dbScan will do much better than K-means. Another advantage is that dbScan naturally identifies outliers, or points that don't belong in any dense group. This is extremely valuable in cybersecurity, where those odd one-out points, those anomalies, might represent new or suspicious behavior. Hierarchical methods for clustering take yet another perspective. Instead of trying to form a fixed set of clusters, they build a hierarchy, or a tree of relationships between data points. At the bottom of the tree, each data point is its own cluster. As you move up, similar points merge into clusters, and clusters merge into larger clusters, until eventually everything is grouped together at the top. The result is a structure called a dendrogram. This method is useful when you don't just want to know what clusters exist, but you also want to know how are those clusters related. Maybe in malware analysis, for example, hierarchical clustering might reveal that several small families of malware are all related to a broader superfamily. Of course, this applies to cybersecurity in obvious ways. There's that malware analysis. Every week, a security company would receive thousands of executable files with potential examples of malware. It's impossible for a human analyst, once we get to a certain number of those, to actually label all of them by hand, but clustering provides a solution. By extracting features from each file, by extracting things about the file, maybe the size, maybe what functions it's importing, or API calls or network ports that it opens, an analyst can represent each file as a vector of numbers and feed those vectors into a clustering algorithm that reveals the natural groupings. And files that cluster together are likely to belong to the same malware family, even if they've never been labeled. That lets analysts quickly focus their attention. If they see one massive cluster that matches an already known malware family, they don't need to spend time rediscovering it. Instead, they can prioritize smaller or unusual clusters that might represent brand new malware. Clustering is also used, of course, beyond malware. In network security, clustering algorithms can group similar flows together, allowing analysts to spot traffic that doesn't fit any known category. Fraud detection is another area we might use clustering to help identify groups of transactions that follow unusual patterns. Insider threat detection, it can group normal user behavior, and so on. The big picture here is that clustering takes raw, unlabeled data and puts meaningful structure on it. It helps to see patterns where none were obvious, and directs our attention to anomalies, those rare but potentially critical points that fall outside the crowd. So when you hear clustering, think discovery. It's about letting the data speak for itself, revealing hidden groupings, and giving us insights into the unknown. When we talk about unsupervised learning, one of the most important tools we need is dimensionality reduction. Think of dimensions here as the number of features in your data set. The number of columns in a spreadsheet might be the number of features. So a single row of the CIDS 2017 data set, for example, might have over 80 different measurements about a single network flow. How many packets were sent, how long the connections lasted, average packet size, number of TCP flags, and so on. In more advanced cybersecurity data sets, you might even have hundreds or thousands of different features about each row of data. So, of course, that's the problem. Humans can't visualize beyond 3 dimensions. Scatterplot shows us 2D. Some creativity, we can get that into 3D, but once we hit about 80 dimensions, our intuition breaks down. That's where reducing those dimensions comes in. It lets us compress the data set into fewer dimensions, usually 2 or 3, while trying to preserve as much of the original structure as possible. That makes patterns visible to us and often makes downstream algorithms like clustering or anomaly detection run faster and more effectively. We have 3 techniques that we talk about here within this slide. Principal component analysis, or PCA. It's one of the oldest and most widely used dimensionality reduction techniques. Imagine that you have a cloud of data points floating in a very high dimensional space. PCA finds the directions called the principal components along which that data varies the most. These are like new coordinate axes rotated to capture the greatest variation. Then instead of keeping all 80 dimensions, we keep just the top 2 or 3 principal components. Beauty of PCA, of course, is that it gives us a compressed view of that data. It still reflects the most important variations within that data, which is important in cybersecurity. We might reduce dozens of traffic features down to just 2 axes, letting analysts plot flows and immediately see whether attacks fall into different regions than what we would call normal traffic. TSNE, or T-distributed stochastic neighbor embedding, is another thing that we talk about when we're talking about reducing dimensions. PCA is linear, but what if the real structure of the data is more curved or more complex? That's where TSNE comes in. This method focuses on preserving local neighborhoods. In other words, if 2 points were close in a high dimensional space, TSNE tries to keep them close to the 2D or 3D map. It doesn't care as much about long distance relationships, but it does an excellent job of showing clusters. If you feed TSNE a data set of network flows, you might see groups of points forming islands. Normal traffic would be one of those islands. Scanning traffic, maybe another one. DOS attack denial of service traffic might be somewhere else. TSNE helps to plot things that are often something that we might do when we're just learning about dimensionality reduction, because we can see how attacks separate from normal behavior. Last one we'll talk about is UMAP, or Uniform Manifold Approximation and Projection. UMAP is a newer technique. It's often seen as the successor to TSNE and tries to get the best of both worlds. It preserves local structure like TSNE, but also keeps some sense of the global structure of data, meaning distances between clusters can be more meaningful with UMAP. UMAP is also generally faster and scales better to very large data sets, which we frequently have in cybersecurity. You might have millions of log entries or flows. UMAP can give you a 2D map where entire traffic types, normal, suspicious, or unknown, emerge as distinct regions. Analysts can then focus attention on small, dense clumps of unusual activity. The big idea is that dimensionality reduction acts like a translator. It takes high-dimensional data that's invisible to us and translates it into a map that we can see and we can reason about. Once we have that map, we can layer on clustering algorithms or anomaly detectors or simply use it for visual exploration. For example, suppose you have 80 traffic features, 80 columns in that spreadsheet, and reduce it to 2 dimensions using UMAP. When you plot the result, you might notice one small cluster is off in the corner. Investigating further, you discover that this group corresponds to a botnet or a command and control channel that's invisible if you just look at the raw logs. That's the power of dimensionality reduction in cybersecurity. It turns overwhelming data into something our brains can actually grasp. Let's look at a case study then of network anomaly detection. Imagine that you are a security operations center analyst responsible for monitoring network traffic within the enterprise. Every day you get millions of connections and they pass through firewalls and routers, the normal traffic there, but you don't really have labels to say this was an attack or this was normal. Unsupervised learning allows you to model a baseline of what normal traffic looks like. Over time, the algorithm learns that web traffic usually occurs on certain ports and that login requests follow predictable time patterns. And of course, the data transfers themselves have certain size distributions that we would consider to be normal. Now imagine suddenly an unusual burst of small packets floods the network from thousands of unique IPs. That doesn't match the baseline, of course, at all. System flags it as an anomaly, and analysts can then quickly realize that it's the early phase of a distributed denial of service attack, or DDoS. By catching it as an anomaly without ever having seen that exact pattern before, defenders can begin to respond to that potential DDoS and take steps to mitigate. Another case study that's an example we would use is insider threat detection. Unlike an external attack, an insider threat is notoriously difficult to detect because employees have legitimate access. So rules that we might do like block all database queries, well, they can't apply to an insider that has the ability to perform database queries. Unsupervised learning models can establish behavioral baselines for us, and they can make behavioral baselines on a per-user basis. For example, if someone usually logs in between 8 and 6 and maybe accesses payroll records because they work in the payroll department, they normally don't send more than 20 emails on a given day. If suddenly they're logged in at 3 in the morning and starts querying R&D, research and development databases, or attempting to query those databases, maybe starts to transfer significant amounts of data, well, then we might want to flag that as being an anomaly. The important thing is that this doesn't require unlabeled insider attacks. We can't label what an insider attack would look like necessarily. That would be quite rare to do. Instead, the system's learning normal behavior and spots the abnormal. Maybe we can later on take an analyst could go through and classify that traffic as normal for a certain time of year. Maybe payroll department's doing something with taxes, or has to, as part of their job, perform some type of activity that's cyclical in nature. Happens once a month or happens once every 2 weeks for payroll, or whatever the case may be. So we talked a little bit about some of the cybersecurity applications here for unsupervised learning specifically. We talked about anomaly detection. We talked about clustering, malware, insider threat detection. We haven't really talked about DNS queries, and that's another area where we might use unsupervised learning. We might be looking at the DNS queries that normally happen during the day, and then suddenly if there's a cluster of DNS queries to new domains, those domains might be representative of something we want to watch. Or if there's a certain number of queries that we would have on a given day, which of course would vary, but then suddenly there's all sorts of new queries that are occurring on our network, it might be representative of an anomaly that we want to take a look at. There are limitations, however, for unsupervised learning. It's not completely magic. It does have real limitations. Clusters don't always correspond to meaningful categories. You might have a clustering algorithm that would group malware into something else other than by threat family. It's not really helpful to, not really always helpful when we think about using unsupervised learning to access or to analyze malware, because we might be, of course, not distributing malware ourselves, but we might be doing code obfuscation on our JavaScript or something like that, and that's going to throw off an unsupervised learning algorithm because it's going to look like malware. That's one of the techniques that they might use. It might create a group, and we then real code obfuscation, real malicious code obfuscation gets grouped into there along with our normal obfuscation that we do on our JavaScript before sending it out. Or simply minifying that JavaScript might also appear as obfuscation and get grouped incorrectly. So the methods are sensitive to noise. The log entries, maybe the log entries, something that we ran a scan on our own network. Well, that's noise within there because that should be Normally, we would label that, if it was a human going through and labeling it, we would label it as normal traffic, or we would remove it from the logs entirely. But in an unsupervised scenario, that port scan is included within the model that's being worked. And so the training is happening on data that we know is just noisy. It's not really related to what we're trying to get at. So that false positive and human in the loop, those are all limitations around unsupervised learning, because we do need to be monitoring what the AI is doing when it is attempting to learn on its own. So we almost always would require the human in the loop, the human to check over what the AI thinks that it found within unsupervised learning. When we're looking and thinking around unsupervised learning, then some key takeaways. We're looking for unsupervised learning to help us find structure in data that's not been labeled. We haven't classified this data yet. We need help classifying this data. And that's where unsupervised learning comes in. Two main pillars of unsupervised learning: clustering and dimensionality reduction. Both of those we've discussed here or a little bit earlier in this video. And unsupervised learning is crucial for anomaly detection, and insider threat detection really helps in those areas, but it is limited. Sometimes we need to spend extra time interpreting those results and noise and so on, and also false positives that can occur. Let's then compare supervised versus unsupervised learning. If we think about supervised learning, it's going to have labeled data. It's going to be classified, and we're going to be able to run classification style tasks on it. With unsupervised learning, we have unlabeled data. We're attempting to discover the structure of that data and get help discovering that structure. A phishing filter might be used for supervised or with supervised learning, whereas anomaly detection might be used for unsupervised. That's not always the case. We can use either a little bit interchangeably. It depends on exactly what it is that you're trying to work with. But we might use unsupervised learning when we have labels that are available and reliable, when we have clear categories and values to predict, and we have repetitive and predictable tasks related to that learning. We might use unsupervised learning when we don't have the data labeled. We're not exactly sure what it is that we're working with, or what an attack versus a non-attack might look like. We want help finding that. We're trying to discover or explore the large amount of data that we have in cybersecurity. We're looking for novel or unexpected behavior in that, and that's why unsupervised learning is great for anomaly detection within traffic. We can also use hybrid approaches, semi-supervised. We have a mix of labeled and unlabeled data, and we're working back and forth with that model in order to determine what the labels should be. We might cluster that malware. We might use an unsupervised means to cluster malware, and then we might go through and label the different clusters once we discover what exactly is in there. So that's a hybrid approach common when we're working with large language models and when we're working with machine learning, generally speaking. But of course, we have challenges that we encounter with when we're working with machine learning and working with AI and building AI. We have a data imbalance. Think about that data imbalance as being, we might have great data and detailed data about a network flow. We might not have great and detailed data about an attack that occurred or attacks that are occurring somewhere else that are very similar to ours. So we just don't have that. We don't have all of the information that we might want in order to be more successful at machine learning and at building our model and at discovering cybersecurity threats and working with them, working to prevent them. There's a huge cost to labeling of the data. Think about trying to label a network flow, which is fine if we have 10 rows. It's fine if we have 100 rows. It's maybe fine if we have 1,000 rows, but there might be some inaccuracy once we get above a certain number. But even 1,000 is something that happened while I was working on this sentence. 1,000 different traffic flows might have occurred on any given network. So we can't possibly go through and label all of those. There's a high cost to labeling. And then there's a drift with the concepts around machine learning, making sure that we're using the right algorithms at the right times, and then being able to integrate machine learning and AI into our workflows. If we have a workflow, we want to make sure that we're integrating machine learning and AI in a way that makes sense, in a way that's cost effective and effective at how it basically helps us with our tasks. It doesn't hinder our tasks, it doesn't slow us down. We want to make sure that we're using the AI and using the language models and machine learning in a way that's conducive to improvement rather than reducing or making things more difficult. So in summary then, key takeaways when we think about machine learning. Well, we learned that supervised, if we think about supervised as already having labels and think about unsupervised as not having labels, we're discovering things about the data with unsupervised machine learning. And each one of those, supervised and unsupervised, has its own strengths and limitations. In cybersecurity, we need to blend both supervised and unsupervised learning. And there's challenges around using machine learning within cybersecurity, and we talked about those as well. Let's talk about data sets in machine learning. We have first the definition of a data set, and I'm going to briefly go through these slides because I want to talk about, we'll see examples of this in the lab that's going to accompany this lecture. So simply put, a data set is a collection of data that's organized for analysis. Think of it as a spreadsheet. I've been using that example within this and previous videos. We have rows, which are maybe considered records, and columns, which are maybe considered features. Each row of data might represent a different log entry, a different line in a text file, and so on. And then each one of those columns corresponds to something that's found in that data file. Maybe one column or feature is the timestamp. Maybe another column or another feature is the source IP. Maybe another column or feature is destination IP and port and so on. Each one of those would be considered a column within our spreadsheet or a feature. And data sets then are the foundation for machine learning, training, and evaluation. So that wraps up this video, and it talked about supervised, unsupervised learning. This video was the focus of, this video's focus was unsupervised learning. But there'll be a lab to accompany this video, and I hope you enjoyed the video, and thanks for watching.